Hello boys and girls. In this video I want to talk about predicativity and impredicativity, a notion that's maybe not as familiar to people as it should be. Roughly, this is about definitions, classifications of definitions, and in particular sort of vicious circles in definitions. And as such, it relates to a bunch of classical mathematical logic paradoxes. It relates to how to set up theories, like set theories or theories of arithmetic. But in principle, it's really just a classification or feature of the expressions that we want to use to do mathematics. And it has a huge history in the last, 150 years or so. And it's worth talking about. It's maybe lesser known in more applied math circles, and by applied I mean everything that's not pure logic. And this is because it is informal in the sense that that's a concept that should apply to a broad range of systems, right? We speak about what we want from definitions, and so one could specify more concretely what it means for a particular system, and I do that in terms of quantifiers in this video. But it's clear that the idea also can be generalized to other systems, and in that sense, it's a metalogical concept. But okay, so how I will do this is I have here this text. After I give you an example and point you to the related link, as always. I show you some papers that I read in the last 2 weeks and so on. I will go through this text. It should maybe take half an hour or so. But I decided, it's a little bit complicated to talk about this subject because I cannot really just put their formula and explain the formula. It's more like a verbal kind of video in this one. So nevertheless, I will start with an example. So here we have a super common situation, right? We define subsets of natural numbers. We want to define a set T, and we define a set T by specifying which elements should be in this set, right? So to make this interesting, it should be an infinite subset of the natural numbers, right? We say T is all natural numbers such that, and here we have some predicate. This is some expression, for example, this capital phi could be this number n is a multiple of 7, right? So 14 would have this property being a multiple of 7, or 21, and 70 would be, and so on and so forth, but the number 10 would not, and so on and so forth. So then in this case, this would be some property about the natural number in question would either be true or false. And then if you say, for example, capital phi means this number is a multiple of 7, then we would understand this set T to be all the numbers that are multiple of 7. So the number 21 is there, for example, but number 20 not, and so on. Okay, so this was just an example of some predicate that I just made up on the fly. And here we want to now restrict ourselves to a particular form of predicate. This predicate, this is basically, this predicate is basically, it gives a definition for the subset, right? The subsets of natural numbers. And we want now a predicate that includes this sort of sub-expression where we say for all subsets of the natural numbers. So for example, again, T is defined as all natural numbers such that for all subsets of the natural numbers, lower phi of n and s hold, where this is another property which might be true or false, provable or not provable, provable or disprovable, that has these two parameters, the natural number in questions, about which we want to decide whether or not it's in a set or not. And then this whole expression forms a statement which is true or false for this natural number is. Okay, and so for the from the concept of predicativity that I will give a course description in a second, this might be problematic because now let's say you take the following approach to specifying subsets. You say you want to go through the natural numbers, right, and find out whether or not a particular number, number 0, number 1, number 3 is actually in the subset T. You want to kind of assemble or construct, let's say, this T, and you say, okay, number 0, is it in there? To evaluate whether or not the number 0 is here, you have to find out whether this statement holds, right? But a problem here is that this universal quantifier ranges over all subsets of the natural number, including the thing that is just being defined, right? And so you say, hey, is the number 1000 or the number 1001? Are these numbers here in this subset? To find out whether a single number is there, you have to make a judgment about a statement that already involves all subsets of the natural numbers, including the one you define for which you just want to find out whether or not something is in there or not, right? So there is a sort of cycle. If you say you want to construct T, then this might be problematic. I will then later come to some proponents or opponents of these sort of considerations. So for example, apart from the really the school founders of constructivism that I mentioned in a previous video, there are people who Weil, who Hermann Weil, who really became convinced that it's a relevant question to ask. For example, is this a coherent definition in the sense that we don't have these circles in our definitions, or if we maybe find ourselves wanting to define a subset of the natural numbers T like that, is there maybe a little bit a more straightforward definition of the same subset, right? Because different mathematical objects can have different definitions, to get rid of this impredicativity. And motivated was this especially by the classical issues at the beginning of set theory, Russell's paradox, and so on, which we will also get to in a second. These problems were discovered, then predicativity or impredicativity really was blamed, in particular for the issues. Then there are then many for this particular problem in particular, like the foundations of set theory. Different solutions were proposed, and then we end up with various set theories, for example, Zermelo-Fraenkel, which solve it in a particular way. But nevertheless, even if that was formally resolved, as to some good level as we understand it, this notion of predicativity still lingered on, and then there was still research on this sort of notion. Okay. And so that example, having been stated, here is a sort of definition of impredicativity. Here we say a definition is said to be impredicative if it generalizes over a totality. In our example, it was this for all subsets, to which the entity being defined, in our case this T, belongs, right? And this is really not just about set theory, really. We will see that, for example, even in standard arithmetic, which is not a priori related to sets, questions of impredicativity have been raised. But I will get to that pretty much at the end of this video. Yeah, so the nicest way that one can clearly see to resolve impredicativity would be to make sure that all definitions are sort of stated as constructions from below, right? Where you don't have these universal quantifiers, but where you only use, in this case of sets, where you only use sets which are constructed, are assembled from objects that we already understand in their totality, right? So in this example, we write down the definition, and this is then an abstract definition, but we might not know much about which elements are really there, so we don't understand the set T in its fullest. And to be very conservative would be to say, everything that smells anything like an impredicate definition we don't allow, and we only allow definitions which plug things together, like the hereditarily finite sets, where you construct sets from other finite sets down to the empty set, and everything is finite and everything is very explicit. I made a video about this in the past. Okay, so this is the sort of problem, and we will in the video see where this idea pops up. Lastly, I'm not 100% sure if I already said it in this video. I don't think so. So I want to emphasize that this is, as we discussed it so far here, a feature of the definitions themselves. It's a feature of how I define the mathematical objects. It's a feature of the definition and not of the object necessarily itself. So it might be that there is a complicated definition, an impredicate definition, or an ugly definition for some other particular logical or synthetic property that we don't like, but the same definition object, same with respect whatever our theory says that equality means, the same object might be definable in a nicer way. For example, it might be definable in a predicative way, and there was some research then on what kind of math for a particular notion of impredicativity can we make predicative. Okay, so that said, I will go through recommendations. This is not a recommendation. The Wikipedia page is not great and not particularly long. Also, it has this sort of bias talking about the history and in relation to Russell. So Russell found his paradox. Here there is a report of the conversation with I think with Frege even, and then in the subsequent years, Russell, he wrote this Principia Mathematica, where he bases mathematics on formal logic, and changes the book a bunch of times and makes propositions how to make things nice and to avoid these so-called vicious circles as he defines it. So Russell comes up with this concept of, maybe it's also explained here, vicious cycle property, and then postulates it away in various forms and so on and so forth. But okay, this is a kind of historical context. We are going to be a little bit more modern in this video. So there is a nice 35 pages paper that I wrote 2 weeks ago by Pfefferman. Pfefferman is a logician who, he deceased already, but is an interesting person because he did a lot of research on these matters. I want to say in constructivist formal logic, but he is not as I understand it, the direct he's not an ideologue or anything. He just researches this and is of course has his opinion, but he has this sort of agenda that's I cannot really pin it down, but it's interesting to read. I read this article. I read into various other articles. He is one of the guys the editors who assembled the collected works by Gödel, who Gödel left 1 billion letters. So this is these tomes of Gödel communications, and I guess you can get a lot out of it. And he wrote about Gödel, obviously then having all this knowledge, probably having read all the Gödel letters to various communications to various mathematicians over the centuries. Or at least in this Gödelian century. So I recommend not just this paper, but look out for this guy's work. Okay, then there is the Internet Encyclopedia. There is more or less a nice, quick overview of impredicativity. You might, if you want to read that, it's kind of a short example of impredicate definitions, where again impredicativity is not like formally defined in that sense that, you know, we say, you know, a real closed field is formally defined. We can tell you exactly what it is. Impredicativity is kind of the notion, this vicious cycle notion, I think I made clear in this example already. And then it's the question: how strict do you want to be about it? What do you want to consider potentially problematic? And maybe you watch this video and think, well, as long as it seems that things are consistent, it's okay. Then you have no bias or no like conservatism in yourself anyway. But of course, we can never know if something is inconsistent or consistent. So also these things, like, I'm motivated also by the fact that the more conservative you formulate things, the more likely it is that you can actually implement these things, I would argue. Okay, so there's that. Then there is this woman, Laura Crosilla, who wrote various texts, I think, about predicativity in mathematics. Here's one article, which in particular, if I recall correctly, relates to, I have here my notes. This is the text that you just read, and I have here some extra notes. Yeah, so this article and her work is about inductive definitions in particular. This paper is about inductive definitions in particular, and whether or not definitions which are a priori possibly impredicative can be restated in a predicative sense. Okay, then here is the talk slides from her. This might be similar content. Related to that, this sort of Pfefferman sort of research is also reverse mathematics. If you have never heard about that, that's also very interesting. This is basically the research by people like Friedman and Simpson, and there's also a book that I read some years ago, which is very nice. This is about taking arithmetic, so just, you know, numbers, or something which is for sure math, and they, I think, choose the second order system. So you have not a set theory, but just arithmetic, but second order. So you can also speak about the predicates in a formal sense, and then they take some theorems and look, hey, which like subsystems of arithmetic, strong subsystems of arithmetic with which axioms are actually necessary, to prove that. This is basically a kind of don't assume too strong axioms, but instead take this result and see what you actually need to prove that. And in that sense, it relates a lot also to this the paper I just had on last, where this professor asks, hey, what is actually necessary to maybe define these things? Maybe you can get rid of this naive impredicate definitions, and this is very much related to that. Then there is a book called Predicative Arithmetic. As we will see in this video, there is an argument to be made that the induction axiom of piano arithmetic, of hating arithmetic, has an impredicative character. I mean, a few people also historically would attack the natural numbers and say the God-given natural numbers, we take them for granted. And a lot of discussions about impredicativity are also from a background where we say, assuming the natural numbers, given that the natural numbers are fine, and then we only criticize everything that comes after, all various axioms that come after. But here, for example, this Edward Nelson, he develops basically arithmetic, piano arithmetic, but without this induction scheme. I will make a note at the end of this video in what way natural numbers, the definition of natural numbers and its standard like proof features, proof toolings are potentially impredicative. I'm of course motivated by constructive set theory. In the last month, I added like 5,000. I just set in because it's still like semi-quarantine time. I just went to Starbucks and I wrote like 10,000 characters. Added here, and if you go here bounded, then you will see this is a lot about like the Atzel's constructive Zermelo-Fraenkel. He has as a main feature that you bound the quantifier in the axiom of separation to not have this, quantification over the totality of things, including the things we want to define. In that sense, CFC is a more predicative theory than, for example, intuitionistic Zermelo-Fraenkel, which is just Zermelo-Fraenkel without the law of excluded middle. Okay, so that's that. I will definitely in future videos eventually come back to constructive set theory. Then the axiom of specification. This here is the axiom of, here the article is called Axiom of Specification. And this is really also about like the specifying sets using predicates, and that's also why it's a scheme. It should work for all predicates. It actually sort of ranges over all predicates, even if you're not in second order but first order logic. And then there's these various names, and here the viewpoints already get in. So you have axiom of specification. This is how the article is called, but also separation. If you reformulate it as it's done here, where it's really about cutting out sets from other already existing sets, to avoid this some problems, aka Russell paradox and so on, or subset axiom scheme, or axiom scheme of restricted comprehension. Because if you don't tweak it the way this is done here, and this axiom is also then used in Zermelo-Fraenkel, if you don't restrict it, then it's just an axiom of comprehension where you say, hey, if I can comprehend, so to speak, this that this predicate specifies something, some set of natural numbers, then this also gives a coherent set that is specified by it. And the naive approach to having this comprehension, as I like to say, like grabbing the sets from the ether just by writing down the predicate that ought to specify it, gives you problems, and then that's why you tweak it and restrict it. In constructive Zermelo-Fraenkel set theory, as I just saw on the page, you restrict quantifiers. And what you do here, and that's why it's also called axiom of separation or subset, is, I don't have to understand this right away here now, but that you add this for all A, and you just cut out elements from this A. So this clause, this X is already given as an element of something existing that's not there in a naive comprehension. Okay, hope that makes sense. We will get in a second to back to general comprehension, and then maybe I leave this tab open for comparison's sake. I made a video about constructive set theory 9 months ago. A lot of this is now already in the Wikipedia article, although there's more. You might be interested in that. Also set builder notation. This is like my least viewed video. It must be super boring sounding. It's probably also a little bit boring, but I thought it worth it. It's kind of a formal discussion of set builder notation that we will also come to in a second here. Subscribe to the channel, of course. And what I will not discuss in this video, I know a bunch of viewers of mine are programmers, Haskell, Cog, Acta, and so on. This notion of predicativity, impredicativity also plays its part in type systems. For example, here's a page on here FTP Haskell, where they talk about impredicativity. And here, I will not go through it, but you here have this for all, and then discuss how the type system is set up, whether or not you can have the object being defined part of this Haskell for all statements. Here in this context, it's predicative, but then they also speak about various other setups that are related to Haskell where they are impredicative and so on and so forth. So this is one page. You have this page in the bottom. There are two more programming-ish texts. So there is a System F article where predicativity is mentioned at least, and then similarly this paper. You will find them below. Okay, so these are my recommendations. I will now go back and get at it a little bit from a historical perspective, and therefore we come back to set theory, right? Okay, before that though, I like when I made this the preparation for this video, I sort of made a list. This is just like some notes that I did. I give no guarantee of accuracy of classification, but here like I give you just some names that you can associate them vaguely in the sense that I came across them at least with these branches. But again, somebody who knows more history and knows actually the opinions of these mathematicians and logicians might have a better categorization than what I present here. So beware. Okay, you had before the turn of the century, right? You had from maybe 1860, 1890. That was the time when Frege, Russell communicated, and Cantor eventually made the set theory, a younger Cantor. So these are what I want to call logicians. Of course, Cantor actually got into set theory by looking at trigonometric functions, funny enough, and like coming up with the idea of ordinals and so on and so forth. Peano, of course, also like very early axiomatization of natural numbers. And I want to correct this here. So this is, of course, a Peano. Hilbert is then also known as formalist, and he has, for example, this famous dispute with Brouwer, who is like a hardcore constructivist, a pupil of him. Russell, and then Zermelo, who did a major work on the formalization of set theory. And I mentioned Zermelo frankly already in the last video, in the chess video actually, from 2 weeks ago. Okay, so then you have the more like extreme constructivist, the finitist. How do you say finitists? These are better known, more or less, people who at least at one point voiced their opinion in pro-finitism, and I wanted to mention them here. Memes included. Then, okay, that said, here we have logicians, finitists, we have some extreme opinions, let's say, and people who are like genuinely like careful, generally conservative, or generally judgmental about all too free definitions in mathematics, were famously Poincaré, and who is like also of the older caliber, like more in the early stages here. Although of course it can influence algebraic geometry, algebraic topology, and so on and so forth, like Hilbert, a very general mathematician. But then, for example, Brouwer, constructivist, I make a question mark here because it's not like constructivism and predicativism necessarily have to go together, right? I mean, you can see, of course, a tendency that if you favor one of the things, you might be not opposed to the other because it sort of relates. Both are conservative in a sense, and I mean conservative not in a bad way either, right? It's like it is not like you. I often hear this the idea of people where they say, oh, if you throw away the law fix to the middle, then you restrict yourself. But this of course not true, because then if you don't have to exclude the middle, then you cannot prove the same theorems, but you can possibly prove other theorems. You can add more axioms, you have more models. It's actually a richer mathematics. If you have less constraints, then you have a richer mathematics. But okay, let's not get into that here. But in particular, I want to mention Weil, who had his own take on predicativism and wrote a book actually on that called the Continuum, which was super famous, like influential also. But eventually he like sort of said, now I will just go with Brouwer's approach, because like I don't know what exactly all his reasons were, but he like jumped on board with him. In particular also because Russell, who had his own solution to Russell paradox and so on, he basically invented type theory to get around these issues. And Weil was initially a fan of Russell, but then eventually come to the conclusion, that's not really practical enough, the system that Russell paints. And then here are some other people, for example, Myhule was one early constructive set theory guy, like I think 70s was his work, who also like says we start with natural numbers given and then has to do some set theory axiom around it. Then some critical words towards predicativity were coming from Ramsey, as we will say, Zermelo, and also Gödel, right? And so I think I have not said that when I discussed this year. We said this definition of T is problematic in the sense that to construct T, you have to know T. This is the vicious circle fear that this might get into problem, and there might be like definitions where this doesn't really work out, especially if you think of the sets as being assembled. But the kind of Gödel argument, the counter argument, Gödel was like a person who argued for very strong, like he said, there are some mathematical problems down there, and we ought to solve them by imposing like big cardinal axioms that decide them. Like for example, the continuum hypothesis. Like he was like, there's a mathematical problem, and to solve these mathematical problems, if it's not independent of the system, then you have to get from above, and in the stuff that's more mathological, interesting, you adopt some natural axioms to search for them, so he has this kind of view where he has this sort of Platonic view that everything is already okay. We just have to find the right axioms, and so he has this following argument. He says, well, I'm paraphrasing here, obviously, because I don't want to put words into Gödel, but basically the idea is that, hey, the mathematical objects are already there, and it's okay to make whatever definitions like that, because we like the only thing that is required is that the definition is sort of coherent and like fits onto the objects, the mathematical objects. They are not assembled or constructed, but they're already there, and it's another question whether or not we humans can then find out what have we actually defined here from all the things that are actually already in Platonic existence. So it's not clear that we can compute what is in there, for example, but the definition is unproblematic in the sense that it just cuts out from the reality of the Platonic object. So the number 10 might be coherently part of this set, if this set is coherently defined or not, and the definition is what it is, and we don't need to actually in our process as a mathematician construct the objects. And so this is not like, this is basically the everything is already okay approach. But again, this is how I understand it from reading up on these historical accounts on the opinions of people. But you can sort of hopefully see where people might have been coming from. Then some names that are like logicians that are researching in these people. I don't really know what their stances are. These three names here. If you are into computer science, you know Kleene. He has so many important definitions and naturally also theorems in computability theory. And then Kreisel and Pfeffermann are names in mathematical logic that pop up now and again, always. Okay, so that's that for the historical introduction. Now let me go back in history, and now we're actually going to take a look at the Russell paradox thing, okay, and how it relates to the impredicativity issue. So here I give you a sketch of class notation, right? You have there are many like set theories. Let's consider first order set theory, and in, for example, Zemelo-Fraenkel set theory, this is written down in first order logic. So you have predicates and quantifiers already as a concept. You might define axioms as axiom schemas, where you say for all predicates, we take this as an axiom. This is a kind of a halfway through. You actually quantify over predicates. So say for all, like for example, in the axiom of specification here, you say for each formula the following thing shall hold. So this is an axiom schema. And so here you have for each formula, right? This is already like a quantification over predicates, but you only do this. This is still considered first order logic because you only do that in the axioms, and you don't during the runtime of your computations or anything say for like do quantifiers over predicates. So it's not second order in that sense. So you have this we have predicates in the logic with which you do your first order set theory, and then you introduce basically informally in Zemelo-Fraenkel theory anyway this class notation. You say, okay, to say that this is the class brackets. Okay, you say that if X is in the class which contains all the elements for which psi holds, right? Then this just means here, the way I ramp it up here, that X is an element of the set of all things for which psi holds. So psi also holds for X, right? I hope that it kind of makes sense. If in this direction, if X is an element of the set of all elements for which psi holds, then this just expresses that X also has this property. Otherwise, it would not be in this class. Sorry, it's class here, not set. And otherwise, if for X the property holds, then X is in this class of objects for which a property holds. Okay, this is like kind of informal class notation to go back and forth there between these predicates. And in a way, in set theory, you give the axioms that specify what classes you could say when an informal collection actually forms a set. And then once a class is a set, once you have established that the collection a priori specified only as a class is a set, then you can quantify over it in the sense that quantifier ranging over sets for all X and so on. In that sense, then also range over the predicates, right? In a sense, the set theory is a trick to specify a way of having a possibility to range over some predicates, right? Because the axioms of set theory specify which classes are sets, which classes are in the range of our quantifiers, because the quantifiers only go over sets. And there's also this sort of correspondence between sets and the predicates that define the sets, right? And if you quantify over the sets, then you sort of quantify over particular predicates as well. Okay, so that said, here we have like in first order logic with the for all X. If we now go down to just sets, X is just the set here, right? Everything that's part of like in Zemelo theory anyway, a class cannot be a member of some other class, and so if I write that, then I speak here of X of sets. So I can say for all sets, this is basically the statement that I just made in a formal sense. This then works. This sort of as an axiom, as a comprehension. This would be like the naive comprehension axioms that set theorists started out with. They said, Okay, we say that for all x and for all specifications or predicates, this is equivalent then to some set that is the collection of all the elements that the predicate holds. And this in the end does not work out for the reason we see below. But here we have this set class correspondence, right? And so here I go with this futile approach, this naive approach that is then shown by Russell to break down. Okay. Just as a note, the existential quantifier, as it is then used in logical calculus, for example, in natural deduction, like the natural deduction calculus for Gensen system and so on. That, for example, if you want to speak type theory, also finds it's constructive, more constructive realization than independent type theory and Monteleuve type theory and so on and so forth. The rule for if you have an existential quantifier is that if you have proven that there exists something with blah blah blah, then you can instantiate this a term with that property and use it further in your proof. I mean, I will not do a course here in proof theory, but if you look at just how to actually formally make use of a existential quantifier, then it works like that. Once you have proven that something exists, then you in the calculus anyway work with objects that have the property where you've shown that something exists that have this property. Okay, and so with the naive comprehension, what you can do is the following. You say there's a y, and I've given this an index here just to emphasize that it relates to this phi. You say, oh, I define just sets by saying, hey, my set is all the elements x for which this holds, right? And if that works, if our axioms are such that this conceptually makes sense, then the statement in first order logic would be the following: there exists a y, like for all psi, for all predicates, exists a y such that for all x, x is exactly then in y if x fulfills this property. Basically, this axiom then says for any predicate that we can come up with, we get there exists actually a y that collects all these elements. And of course, if the predicate is some bullshit, then the set might often be empty because there's just nothing which fulfills the predicate. But here we have this naive comprehension axiom, right? And I hope the name makes sense, naive comprehension. Then like in first order logic, once we write it down, then we have as we do actually in practice set theory, we then go on and would define objects like that. We say y equals, and then we write this expression here. But again, this is just the notation, like as I describe in the set builder notation video. What you actually ought to do, like on a formal level, is just writing down these closed first order formulas and doing deduction. Okay, I'm sorry this is a little bit detailed, and I hope it's not too much over the place, but and hopefully we'll have a payoff in a second. So yeah, okay, I just read it out here. So a priori classes aren't in the range of the quantifier, although once you have proven that a certain class actually is a set, then you have can save the quantifier, you can quantify over it. Proper classes, like this proper is an informal predicate where you say that those are these classes which are generally not proven sets or provable as sets. Sets are those which we can quantify. Yeah, and if you have this naive approach where we say every predicate just becomes a set, every class that we define is actually a set, then the sets are just classes. Then you basically have a sort of second order logic in a way, right? Okay, or higher order logic. And now this naive approach famously does not work, because you can say, hey, what about the predicate x, like the property of x being x is a member of itself, Oh, it's not a member of itself. What do I do here? Sorry. Okay. Then if we plug in this predicate here, right, then this becomes x is not an x. So the axiom says that it's true that there exists a y such that for all x is in y exactly when x is not in x, right? And so what we can do now then, that's why I explained it in such detail, we can then say, oh, there is a y, a particular y, such that for all sets, there is a set such that for all sets this thing holds. And what we then can just do is, oh, if it holds for all sets, then it must also hold for the y, which we by the axiom just demonstrated to, like, instantiated to exist. And then the statement, like, then x becomes y, and then the statement is just y is in y is equivalent to y is not in y, and that's a contradiction. And from this we can have a proof of like, if whatever is true, the other is also true, and this is Russell's paradox, right? Okay, so this failed, like this naive approach failed, right? And now, okay, of course, in Zermelo-Fraenkel set theory, there's then the resolution by saying, oh, well, we just discard this axiom, we just discard a naive comprehension, we go to restricted comprehension, which is then a sort of subset axiom, because in the way that's implemented, I'm also demonstrating that in a second. But let's not jump to this resolution in Zermelo-Fraenkel right away, but let's actually analyze or report of the analysis that happened with this concept. So again, keep in mind, this is the axiom that made the trouble. And so here is the constructive criticism. An issue is that this once we say that if you have the statement A is member of B, right? Then A, like if I call A the smaller thing because it's inside of the bigger thing B, then the idea is, hey, wouldn't it be smarter or like more coherent to say to assemble an object, we want to create a B only with A's that we already understand, right? So to write down A is a member of B, then we see this as a process of like making claims about what B is comprised of. And so we put into B things that we already know, like we construct B by taking already constructed A's, right? We put them into them. And if we make this sort of demand conceptually, then of course a statement like here the x is in x, once this coincides, once we say hey, choose x equals y, or y is in y, y is in y would then be sort of ruled out, because then we would like either we know x already, or either we know y already, and we can make a judgment of this, like say, oh, this is obviously not true, for example, or we don't know anything about y, and then we should not actually be able to judge whether like y is in y. There was no this cannot be part of the process of assembling y if we don't already know y. I hope this, it's a little bit confusing to spell it out in words here, but I hope you see the point. The point is to demand a sort of hierarchy where we say either you define already the you set up the bigger sets and see this membership as just some judgments, or you see it as a sort of assemblage where you already have the smaller things and create the bigger things. But these sort of axioms where these things are like juggled together, it should be no surprise that this leads to problems in a way. And by the way, if you were wondering about predicativity, here you can say, you want to say that the bigger one is predicated on having the smaller one. So here you can kind of introduce this predicativity if you want to read it that. I don't actually know why. I think Russell was it who came up with the word, chose predicativity, but this is one where we are approaching it. Okay, this is a sort of you have to construct things criticism, and can be seen from both ends. Either defining the bigger thing independently of the statements of membership, or you assemble, as I just said. The first thing that is then sort of realized in the type theory, where you define types and then just make judgments about subsets, and you don't create. No. Okay, so this is getting a little bit out of hand because, in this video I don't want to talk about type theory really, but I hope you get this sort of course description of what you can criticize there. I emphasize this because there's this other criticism that is similar, related, but not actually the same, which I want to get at here, namely the kind of syntactic quantifier positioning issue. Namely that you could say, oh, of course this is here a problem, because these quantifier they range over the same thing, right? And so this will automatically happen here, that you have that once you make an axiom like that and you instantiate the object, then of course the definition of the object was already like predicated on the object itself, because then the right next quantifier already has the potential to talk about this y here, right? And so this is this goes then in this bounded quantifier direction, where you actually say, well then just don't use this general quantifier, but actually think smartly about what you actually want to write down here. Okay. Yeah, and then here in a strict sense we could say we can characterize predicativity as then rejecting to range generally over these uncompleted classes, uncompleted infinities, and so on already. Completed infinities. Like there's this book by Paul Taylor called Foundations of Mathematics, which I also really like. It's a little bit difficult to read, I guess, as an intro, but then again, it's also like it is kind of does normal mathematics, but has this kind of type theoretical language that maybe like non-computer sciencey mathematicians are not so used to. So I would look into that. Okay, and then finally here also the Russell's reaction. So he formulated this vicious cycle property saying, whatever contains an apparent variable must not be a possible value of that variable, right? So this is exactly this thing. So this goes over all sets. This is a possible member of that. So if you take this as definition, it might not work. Okay, and then for sure, the one popular approach that kind of worked and people went with is the Zermelo-Fraenkel or Zermelo resolution, where you say, well, the phi in the axiom must be of the form psi in the axiom must be of the form phi and x element of a, but we've already given a, right? And so sort of this is pretty much what you see here. So here we would have we used x and y. Here is x and b. So here we have this, there exists some b or y in our case for all x. And what they do here is they make it work by saying that here's not a general predicate, but the predicate that we actually consider is of this form. But this is general. But here we say that x must already be an element of some specified set, some already given set. I mean, here is also the for all quantifier, but this is sufficient to rule out Russell's paradox in Zemelo-Fraenkel to avoid this problem. So this is one resolution, not as conservative as one might want from the predicativity perspective. Okay. Yeah, as I already mentioned, type theories, which, I mean, there's then many ways to define type, set up type, and I don't want to get into inductive definitions and so on and so forth. For example, the inductive definition of natural numbers in type theories is, I would say, quite different than the first order approach, or with schema and induction axioms and so on and so forth. Although all these things, of course, realize because type theory eventually also proves the same things that are constructively provable in this piano arithmetic. Okay. And the other axiom of separation that I'm currently interested in is this constructive set theory approach, where you actually make just a weaker form of separation. Where you have you can formalize it with a predicate of predicates is bounded, where you say, oh, I don't say for all, for all phi, but actually just phi with a certain, maybe syntactic. Either I formalize it with a syntactic restriction, or I introduce and this is bounded predicate and formalize it this way. But this for each formula is too wild, this scheme. Okay. We are soon through. Just a few notes. So yeah, I emphasized this at the beginning. Impredicativity is a feature of the definition, and there might be others. And of course, then we can say if there's actually no predicative way of defining a concept, we can call the concept also impredicative. Here I give some examples where these things show up. Predicative definitions sometimes involve fixed points in induction or ordinals. This is what really I got from this this paper by this female professor, Laura C., where she talks a lot about inductive definitions. But these are actually sort of logical theories for mathematics that are so little used by actual mathematicians that just from that perspective I have lesser interest. The nice thing about constructive set theory, for example, is that it sort of embeds into the classical one, and so you don't actually change your language when you read a math book. Yeah, okay, I know this. And I really went through most of these points already. Yeah, then there is also, for example, I mean, there's various approaches to actually get at peace with Russell paradox in other ways than Zemelo set theory. For example, there's the Ackermann theory, where similar to the is bounded predicate in constructive Zemelo-Fraenkel, you can say I have this predicate of is set, and you actually state axioms for that. Or you can also formulate Ackermann set theory with a constant symbol V, which ought to be the set theoretical universe. But then you have also classes which might be bigger in a sense than this set, and so on and so forth. And it turns out that this is also a theory which has little axioms. Actually, it's very simple axioms. Basically axiomizes Zemelo-Fraenkel set theory, except you also have a formal notion of classes, but you also have this sort of predicate. and then there's also Gödel-Bernays set theory, which also has a formal concept of classes, but which is different than Ackermann set theory. Okay, and finally, there's also paraconsistent logic, which also gets around, in a sense, to Russell's paradox, in the sense that it doesn't end the theory there if you find this contradiction, because it's paraconsistent. Okay, and so finally, here's some examples which might be considered impredicative, and then also a criticism. So most of these examples that I will give are of the form of talking about a supremum or something like that, a comparison, because these notions can easily be stated in an impredicative way, as we will see in a second. So there's a criticism by Ramsey, a friend of Wittgenstein who died far too young. He's famous for some studies in graph theory. So I came up with this name, I think. But if I ask the question, who in this football team is your friend Julian? What did I write here? Okay, I ask this question and then you give this definition. Well, Julian is the tallest player in the football team. Okay, then this definition is really already also impredicative in the following sense. What to say that Julian is the tallest player in the football team is really to say that for each player in the football team, Julian is the one that has the property that he is taller or just as tall as this player, right? So let's say there's a football team of 11 players. One of them, Julian, happens to be the tallest one. To formally state that is to say, for all the players, so all 11 players, Julian is the one that has the property that he's either taller than them, this player at hand, or he's exactly as tall as him than he's himself, right? You define somebody out of a group by comparison as the maximum. And this is impredicative because the football team, if you say for all players in the football team, this already includes him, right? And Ramsey was like, hey, okay, this is also like formally impredicative, so what's the problem? And this is basically like I say, hey, you're going too far if you demand impredicativity. Of course, this is a nice finite situation, and here you can easily say that sort of could easily be resolved with kind of Gödel's idea. Right? Yeah, okay, the football players are already there, right? It's not like we're constructing the football players; they're already forming this team, and then we can actually go through them. We're not like we are not the act of uttering the definition of this. It doesn't bring the football team into existence. Whereas with mathematical objects, it's more complicated. Okay, along the same lines, there's the least upper bound property in analysis, which is similar. It's also this kind of extremum characterization, and you say all the numbers have this and that property, and then you might say, that's a little bit itchy. It's the uncountable set, and then you say it has this property, and this is kind of making this comparison. And Weil's Das Continuum is like tackling these kind of issues and discussing them to death, I guess. Ordinal definitions, which are then used in proof theory and other parts, are also can have this impredicative character. And then there's also by Pfefferman this classification of ordinals, where you say, up until this ordinal, some big countable ordinal. I think it's countable. You have predicative ordinals, and it's okay with these theorists, they can describe this ordinal, but beyond that, to describe these other bigger ordinals, later ordinals, you actually have to have a theory which has some impredicative characters and so on. Then some more ordered descriptions, so measurability and induction. Right. Okay. So these are this ordering kind of situations, and then finally, I want to mention then how can we consider the piano arithmetic impredicative? Why do people do that? Right. I showed you this book called predicative arithmetic, and the argument goes like this. So if you do pure piano arithmetic, right, you don't start with set theory. You don't say, oh, there's an empty set and then there's pairing and blah blah blah, and you don't model natural numbers by identifying them among this hereditary finite sets. But what you do is you give a first order or second order description of what is a natural number. Okay, what is a natural number? Well, it's characterized by the axioms of piano arithmetic. In particular, you say, this is one approach, getting at it. And the axiom of infinity is actually looking a little bit similar in set theory, but that's beside the point. For example, second order characterization of the natural numbers is the natural numbers are all these objects which fulfill the natural number induction scheme. So it says, and the natural number induction scheme is a statement about properties in the same sense that specification is a statement about properties. So this scheme. So I don't have it open now, and I can try to quickly find it here. Induction. Should have done it up front. Automatic induction. Okay, here. So yeah, here we have it in second order logic. It says for all properties, right? This is in second order logic. You can actually quantify over the piece or size in our case, but for each property. This is just induction. Wait a minute. Let me actually. This is the induction scheme, but this is already quantifying over the natural numbers here, right? But if you have this pure standard approach to defining here, what is, how do I actually define among all objects, mathematical objects of conception, what is a natural number? Then you might start out with, what are the slides here? I saw in the slides they had this example. I think it's a good way of getting at it. Okay, let's check out this here. Oh, no. Sorry for that. Otherwise I might just go with the induction. Okay, last try. Jesus. Okay, well, then in words, the idea is to say that the question is, how do I define the predicate that says that a given object is a natural number, right? You don't say, hey, the domain of this course that I will talk about is already natural numbers, and in the domain of this course, natural numbers, these natural numbers fulfill these axioms. But you actually want to define, hey, what does it mean, natural number? You have a predicate n that says is natural number. And what is a natural number? Well, you say that the standard approach is then to say a natural number is all these objects which fulfill this induction axiom. So a natural number is this object which for all properties fulfills this thing, and the circularity then comes into play when you recognize that this induction, with which in this case of defining natural numbers, right? This is similar to defining the infinite set in the smallest infinite set, for example, in the set theory. This axiom that you use to characterize it ranges over all predicates and all natural numbers, right? And all these predicates might also have also quantifier over natural numbers. And so if you use induction to define the property of being a natural number, then you also have a vicious circle there. right? At least you can argue like that. But of course, most people say, well, the natural numbers, you know, they never did anybody any harm. It looks very consistent. There's Gensen proof and some other nice proof of consistency from various perspectives. So most people say, you know, given the natural numbers, let's study predicativity. But in principle, if you say there's more in the Platonic realm of mathematics than just natural numbers, then what does it actually mean to be a natural number, right? If you don't say a natural number isn't that set, but if you say I want to have a property of is natural number, then how do you define that actually without going over all natural numbers in this sort of induction axioms, if a natural number is something that has an induction axiom? So it finally loaded. Yeah, here's this sort of definition here. It says, in many approaches to the foundation of mathematics, a property n of being a natural number is defined. So if you want this property of being natural numbers among other mathematical objects, then an object is x has the property of being a natural number, just in case x has every property f which is had by the number 0 and inherited via the accessor at this induction step. So if you really want to specify n, then writing down this thing for all natural numbers, where natural numbers are characterized here, is the circle. And I suppose the predicative arithmetic guy doubles down on this perspective, and I have not read the book, but it sounds interesting. Okay, this was a little bit longer than I hoped, but you know, apart from a few papers and a sketchy Wikipedia article, finally there's some resource on predicativity, public service. Okay, take care. I will participate in this MIT algebraic geometry course that is starting up now this week. Maybe I do some videos in that direction. Otherwise, if you're also participating this course and see this video, I mean, chances are not as huge. I don't have that many people who watch my videos to 70 minutes. But if you do and you happen to be there, contact me. And if you want to do exercises together or something, I'm really interested in that as well. Okay, take care.